Hello, welcome to the course on 3G, 4G wireless communication systems. In the last lecture, we completed the example on optimal MIMO capacity, that is power allocation, optimal power allocation for MIMO capacity maximization. We in fact illustrated the power allocation, what was the different powers that need to be allocated, and we also demonstrated the complete transmission scheme, that is what are the symbols that are transmitted and how are they pre-coded and with what powers. I urge you to look at that example again to revise this concept of optimal MIMO power allocation for capacity maximization. Next, we started with an asymptotic capacity analysis of the MIMO communication system and demonstrated that for a specific scenario, as the number of transmit antennas progressively increases, the capacity tends to R log 1 plus SNR, which can also be represented as the min of R comma T log 1 plus SNR, and we said the MIMO capacity scales as the minimum of the number of R comma T, which is the number of receive antennas and transmit antennas. Hence, it increases linearly with the transmit power. That is the reason MIMO results in a significant throughput increase for the same transmit power. Okay. And next, we proceeded to consider orthogonal space-time block codes, or the Alamuti code, which is a code designed for a 1x2 system, that is one receive antenna, two transmit antennas, single receive antenna, two transmit antennas. The channel coefficients are denoted by H1, H2. We said that in the first time instant we transmit x1, x2. So, the system model is denoted as follows: y equals h1 h2 into x1 x2 plus n. We said that if this h1 and h2, that is the coefficients, antenna coefficients, are known at the transmitter, then I can transmit the vector such that x is the transmitted symbol, it is multiplied by the beam forming vector h1 star or h1 conjugate divided by norm h, h2 conjugate divided by norm h times x. And you observe that using this scheme, the SNR at the receiver is norm h square p over sigma n square. So, I am getting the complete diversity order, which is diversity order 2. However, the catch in this system is that these channel coefficients h1 and h2 need to be known at the transmitter for this scheme to work, and that is not possible frequently in a wireless communication system. Hence, we have to design alternative schemes to achieve transmit diversity without the knowledge of the channel coefficient or knowledge of the channel state information at the transmitter, and the Alamuti scheme is one such scheme. It is designed for a 1x2 MIMO system or one receive antenna, two transmit antenna system, and can achieve the complete diversity order 2 without knowledge of the channel coefficients at the transmitter. So, we were starting to look at this. I went through the workings of this also, namely we transmit x1, x2, two symbols x1, x2 across the transmit antennas in the first instant, and the next instant we transmit minus x2 conjugate, x1 conjugate. Since I was short of time last time, let us go over this again, so as to enhance our understanding in regarding this. So, the Alamuti code in the first instant, this is the 1x2 system. In the first instant, I transmit x1 comma x2 plus this is noise. In the first instant, I am transmitting x1 comma x2. In the second instant, what I do is I shift the symbols, I flip the symbols, and I take the complex conjugate and take the negative of one of the symbols. So, h1 h2, I transmit minus x2 conjugate from the first antenna, x1 conjugate from the second antenna, and this is the second time instant. So, this is the second time instant. I am transmitting minus x2 conjugate, where x2 was transmitted previously from the second transmit antenna. I am taking minus x2 conjugate, transmitting in the first transmit antenna, x1 conjugate from the second transmit antenna, where x1 was previously transmitted from the first transmit antenna in the first time instant. Now, what I do at the receiver, I am going to consider y conjugate as a receiver processing, then this system can be represented as h1 conjugate, h2 conjugate minus x2 x1, which simply the conjugate of each quantity in conjugate 2. This can also be, now instead of having a minus sign in minus x2, this minus sign can be absorbed in minus h1. So, this can also be written as minus h1 conjugate h2 conjugate x2 x1 plus n conjugate of 2, and this can also be, now instead of having x1 x2, I can reverse the order of these symbols here. Remember, this is not reversing the transmission, but simply reversing the mathematical order of consideration, which means these coefficients get reversed over here. I can replace this as h2 conjugate minus h1 conjugate x1 x2 plus n conjugate 2. So, I have reduced this transmission in the second instant to this form, and now I can combine these by stacking y1. You can see that the net system model can be expressed as follows, that is simply h1 h2 conjugate h2 minus h1 conjugate x1 x2 plus n1 into conjugate. Okay. So, I have reduced, so this Alamuti, this 1 cross 2 system with this transmission of x1 x2 in the first time instant and minus x2 conjugate x1 conjugate in the second time instant can be succinctly represented by this net system model at the receiver by stacking y1 and y2 conjugate, and this is C1, this is C2. Observe that this is now equivalent to a 2 cross 2 MIMO system. This is equivalent to a 2 cross 2 MIMO system. In fact, observe that column 1 is orthogonal column 2. In fact, you can observe that column 1 is orthogonal to column 2. Let us check that. Column 1 is nothing but H1 H2 conjugate, column 2 equals H2 minus H1 conjugate, and hence column 1 Hermitian column 2 equals H1 conjugate times H2 plus H2 minus H1 conjugate. This is equal to H1 conjugate H2 minus H1 conjugate H2, which is 0. Hence, you can observe that column 1 C1 Hermitian C2 is 0. Hence, these two columns are in fact orthogonal in this MIMO system, in this equivalent 2 cross 2 MIMO system, which the Alamuti coding scheme has been reduced to. The two columns are orthogonal. So, the two columns are orthogonal. Hence, in fact, hence C1 divided by norm of C1 can be employed as a receive beamformer to detect x1. Hence, C1 by norm of C1, that is the first column, can be employed as a receive beamformer to detect this symbol x1. For instance, let us take a look at it. C1 divided by norm of C1, norm of C1 is nothing but H1 divided by norm of H and H2 conjugate divided by norm of H, which is nothing but 1 by norm of H, H1, H2 conjugate. We can also denote this as the beamformer W1. So, W1 is nothing but H1, H2 conjugate, that is column 1 divided by norm of column 1. Now, norm of column 1 is nothing but norm of the vector H1, H2 conjugate, which is nothing but norm of the vector H1, H2, which is nothing but norm of the vector H, where H is the vector H1, H2. For convenience, we can represent it as norm of H, since it is the same quantity. Okay. Hence, looking at W1 Hermitian y bar, the system can be represented as 1 over norm of H. W1 Hermitian is nothing but H1 conjugate, conjugate of H2 conjugate, which is H2, times the system, which is H1, H2 conjugate, H2 minus H1 conjugate times x1, x2 plus W1 Hermitian n bar. Okay. So, what I am taking is, at the receiver I am taking this y1, y2 conjugate, which I am calling y bar, that is I stacked, remember, y1, y2 conjugate to get the equivalent 2 cross 2 Alamouti system model. I am receive beamforming using W1 using W1, which is the receive beamformer. So, I am multiplying by W1 Hermitian. You can see we earlier said W1 Hermitian, W1 is derived from column 1, hence it is orthogonal to column 2. So, this is nothing but 1 by norm H times, you can see this is H1, H1 conjugate plus H2, H2 conjugate, which is magnitude H1 square plus magnitude H2 square, which is norm H square, and this is of course 0, as C1 is orthogonal to C0 into x1, x2 plus n1 tilde. I am calling W1 Hermitian n bar as n1 tilde. Since W1 is a unit vector, you can ensure that the noise variance is preserved. The noise variance is nothing but sigma n square. You can verify that sigma n tilde square is sigma n square. Okay. This we have done several times before. Hence, this equivalent system model, look at this, this is nothing but norm H square divided by norm H. So, this is nothing but equals norm H comma 0 into x1, x2 plus n1 tilde. This is nothing but norm H into x1 plus n1 tilde. This is after beamforming by W1 bar, that is using the beamformer W1 bar. So, I am doing as I am multiplying by W1 bar Hermitian, and you can see now that the SNR at the receiver is nothing but norm H square P1 divided by sigma n square. So, I can use this first, I can use this to because this is free from x2, I can use this to decode x1. The SNR is norm H square P1 by sigma n square. Observe that there is a norm H square in the numerator, hence this results in diversity order because norm h square is nothing but magnitude h1 square plus magnitude, this is square root of magnitude h1 square plus magnitude h2 square. There are two fading coefficients h1 h2 similar to maximum ratio combiner, hence this has a diversity order of 2. Since this scheme has a diversity order of 2, similarly to decode x2, the beamformer W2 is given as W2 bar, that is to decode x2, the beamformer W2 bar is given as W2 bar equals C2 divided by norm of C2. The beamformer W2 bar is given as C2 divided by norm of C2, which is again nothing but 1 by norm of H times H2 minus H1 conjugate. You can verify that this is in fact the beamformer, which is orthogonal to again column 1, because the columns are orthogonal. So, this beamformer is orthogonal to column 1 and helps decode the symbol x2. Right. So, this is again similar to what we did earlier. Now, let us look at a basic example, or before we look at a basic example, first let me go back to the SNR of this Alamuti system. The SNR of this Alamuti system we said is norm h square p1 by sigma n squared. So, SNR Alamuti equals norm h square p1 divided by sigma n square, where p1 is the power allocated to symbol x1. Now, remember the total transmit power is Pt. So, total transmit power is P, which is fixed. Right, total transmit power. Remember our transmit vector is nothing but x1 x2, all right, which means there are two symbols that is being transmitted every instant of time, which means the transmit power has to be split between these two symbols. Hence, P1 equals transmit power of x1 equals P2 equals transmit power of x2 equals P by 2. Hence, the transmit power is split which between each of these streams as P over 2, which means the SNR equals P over 2 norm h square divided by sigma n square, which is nothing but half norm h square P over SNR square. Hence, you can see that Alamuti code achieves the diversity, that is second order diversity, without channel knowledge at the transmitter. However, you pay a price, that price is this factor of half, which results in 3 dB loss in SNR. This 3 dB loss in SNR is compared to either maximal ratio combining, that is having multiple antennas at the receiver, or in fact having channel knowledge at the transmitter. That is, if you knew the channel knowledge at the transmitter, you can again beamform in the direction h1 divided by norm h, h2 divided by norm h, remember, to get the same gain as MRC. However, this Alamuti code, it gives you the diversity order, which is more important in a wireless communication system, however results in a 3 dB loss in SNR. Okay. So, this is the 3 dB loss in SNR, which is the price that has to be paid to gain diversity without knowledge of the channel at the transmitter. As you can see, the columns C1 and C2 are orthogonal. This is not a coincidence, this is by design of the Alamuti code. This is a special property of such codes. The Alamuti code belongs to a special class of codes known as orthogonal space time block codes. So, let me elaborate on each aspect. Alamuti to a special class of codes termed as orthogonal space time block codes. Right. Why orthogonal? Because observe that the net C1 comma C2 are orthogonal. Why space time? Because observe it is coding across space and across time. If you observe, we transmit x1, x2 in the first time instant, x minus x2 conjugate, x1 conjugate in the second time instant. So, this is time and this is space, that is across the transmit antenna. So, there are two dimensions to it, one is across space, the other is across time. This is the antennas, hence this is a space time and there is a block of symbols, it is done using a block of symbols, hence is a space time block code. Hence, Alamuti belongs to a special class of codes termed as space time block codes or orthogonal space time block codes, abbreviated as OSTBC. Alamuti code is an OSTBC, where OSTBC stands for orthogonal space time block code. Okay. Further, observe that Alamuti transmits x1, Alamuti code transmits x1, x2 in the first time instant, minus x2 conjugate, x1 conjugate in the second time instance. Hence, it transmits a net of two symbols x1 comma x2 in two time instants. It transmits a net of two symbols in two time instants. Hence, it effectively transmits one symbol per time instant, that is it transmits x1, x2 across two symbol instances. So, if you see the net rate, which is 2 over 2 time instants, which is one symbol per time instant, hence this is termed as a rate 1 code. Hence, it is termed as a rate r equals 1 code. Hence, Alamuti code is essentially termed as a code, space time block code, orthogonal space time block code with rate equals 1. This is also sometimes said as full rate. This is also termed as full rate code, that is rate equals 1 is also termed as a full rate code. So, allo T is a full rate OSTBC, that is the correct way to describe allo T code, which is a full rate orthogonal space time block code. Okay. Let us take an example of the allo T code. Let us take an example. I want to consider a 1 cross 2 system given by the following system model, that is y equals 1 plus j For this example, I will ignore noise just to illustrate how the columns are orthogonal and how the decoding is done. I am going to ignore the effect of noise. So, this is my 1 cross 2 MIMO system, this is my 1 cross 2 system, this is H 1, this is H 2, these are the two channel coefficients H 1 and H 2. H 1 is between first transmit antenna and receive antenna, H 2 is between second transmit antenna and receive antenna. Remember, there is single transmit, single receive antenna, there is one receive antenna and two transmit. Remember, there is one receive antenna and two transmit antennas in this system. Okay. Which means I can write this as the first transmission. Remember, we are transmitting x 1 and x 2. So, I can write this as y 1 equals 1 plus j 3 plus 4 j into x 1 and x 2. This is the first time instant This is the first time instant. In the second time instant, remember, I am transmitting minus x 2 conjugate x 1 conjugate, hence this is channel 3 plus 4 j minus x 2 conjugate x 1 conjugate. I can take y conjugate 2 at the receiver. So, this is done at receiver. Remember the operation of conjugation, that is the operation of taking y conjugate 2, conjugate of y 2 is being done at the receiver. This is nothing but 1, that is H 1 conjugate 3 minus 4 j, which is H 2 conjugate into minus x 2 x 1. Now, I will shift the minus sign from x 2 into the channel. This is simply a way of writing it. This is nothing to do with the transmission. It is simply a way of expressing this, equivalent way of expressing this. This can be represented as y conjugate 2. So, the minus symbol from x 2 goes to the channel coefficient, which is minus 1 plus j 3 minus 4 j x 2 x 1, and finally, now I flip the order of x 1 x 2, that is I am not flipping them during transmission. This is just simply an equivalent way of expressing them. This becomes 3 minus 4 j minus 1 plus j x 1 x 2. All right. Now, I can stack y 1 and y 2 conjugate, stack y 1 comma y conjugate 2 y 1 comma y conjugate 2, that gives me 1 plus j 3 plus 4 j 3 minus 4 j minus 1 plus j x 1 x 2. So, now as a net result that I have taken y 1, I have done some manipulations on y 2 conjugate, I have stacked y 1 y 2 conjugate. The net system is this 1 plus j 3 plus 4 j 3 minus 4 j minus 1 plus j into x 1 x 2. Now, you can see column 1 equals 1 plus j 3 minus 4 j, column 2 equals 3 plus 4 j minus 1 plus j. Now, you can see column 1, column 2 are orthogonal. For instance, if I take C 1 Hermitian C 2, consider C 1 Hermitian C 2. If I consider C 1 Hermitian C 2, that is nothing but 1 plus j conjugate into 3 plus 4 j plus 3 minus 4 j conjugate into minus 1 plus j, which is 1 minus j into 3 plus 4 j plus 3 plus 4 j into minus of 1 minus j. This is nothing but 1 minus j 3 plus 4 j minus 3 plus 4 j into 1 minus j, this is 0. So, C 1 and C 2 are orthogonal. In fact, we knew that because we proved it rigorously from the structure of the Alamuti system, that is when we stack y 1 and y 2 and some rearranging, suitable rearranging of the terms, we know that C 1 is orthogonal to C 2. Hence, the beamformer for W 1, the beamformer to detect x 1 the beamformer to detect x 1 is given as W 1 equals C 1 divided by norm of C 1, which is equal to 1 over square root of 27 3 plus 4 j minus 1 plus j. You can verify that norm of C 1 is nothing but square root 1 plus 1 plus 16 plus 9 equals square root of 27. Hence, W 1 equals C 1 divided by norm of C 1, that is 1 over 27 square root of 27, 3 plus 4 j minus 1 plus j. Decode, detect, for detection of x 1, you simply perform W 1 Hermitian y bar. For detection of x 1, you simply perform W bar Hermitian y bar. I am sorry, this is actually, so C 1 is 1 plus j 3 minus 4 j. So, W 1 is 1 plus j 3 minus 4 j, that is C 1 divided by norm of C 1. Norm of C 1 is the same thing, square root of 27, and to decode x 1 I employ W 1 bar Hermitian y bar. Similarly, W 2 equals C 2 divided by norm C 2, which is nothing but from this 1 over square root of 27 3 plus 4 j minus 1 plus j divided by square root of 21, and to detect x 2 we have to perform W 2 Hermitian y bar, and that can be used to detect x 2. So, one can perform. So, C 1 and C 2 are orthogonal columns in the equivalent 2 cross 2 MIMO system of the orthogonal space time block code Alamuti code. So, W 1 can simply be derived as C 1 divided by norm of C 1. W 2 can be simply derived as C 2 divided by norm of C 2, and to detect x 1, one can perform C 1 W 1 Hermitian y bar. To detect x 2, one can perform W 2 Hermitian y bar. In fact, there are other orthogonal space time block codes. So, we will see one example of another orthogonal space time block code. An example of OST or an example of another So, we will see another example of an orthogonal space time block code. This is for a 1 cross 3 MIMO. This is for a 1 cross 3 system, which means 1 receive antenna and 3 transmit antenna. So, this is for 1 receive antenna and 3 transmit. So, this is for 1 receive antenna and 3 transmit antennas. So, in this 1 cross 3 system, there is 1 receive antenna, 3 transmit antennas. The channel coefficients or in fact, the channel matrix can be represented as H1, H2, H3. H1 is the coefficient between the first transmit antenna and receive antenna, H2 is the coefficient between second transmit antenna and receive antenna, H3 is the coefficient between third transmit antenna and the receive antenna. Okay. So, this is H1, H2, H3, this is the 1 cross 3 channel matrix or 1 cross 3 MIMO channel. Strictly speaking, this is a MISO channel, that is multiple input single output channel, but in general we can call this as a MIMO 1 cross 3 MIMO system. Now, the space time block code structure, I will write down the space time block code structure over here. It transmits each time instant it obviously transmit 3 symbols, because there are 3 transmit antennas. In the first time instant it transmits x1, x2, x3. So, we will use the similar structure, that this is space and this is time and this is a block in space time, hence this is a space time block code. In addition, if it is orthogonal, then it is a orthogonal space time block code. Here, however, we are also considering orthogonal space time block codes, hence it is an OSTBC. So, first time instant I transmit x1, x2, x3, that is x1 from transmit antenna 1, x2 from transmit antenna 2, x3 from transmit antenna 3. In the second time instant we transmit minus x2, x1 minus x4. In fact, there are 4 symbols in this block code, x1, x2, x3, x4. So, we are transmitting x1, x2, x3, x4. In the second time instant, we transmit minus x2 from transmit antenna 1, x1 from transmit antenna 2, minus x4 from transmit antenna 3, and I will give the rest of the block minus x3, x4, minus x3, x4, x1, minus x4, minus x3, x2, x1 conjugate, x2 conjugate, x3 conjugate, minus x2 conjugate, x1 conjugate, minus x4 conjugate, minus x3 conjugate, x4 conjugate, x1 conjugate, that is I am transmitting minus x3, that is in time instant 7. Remember, this is the 7th time instant. In the 7th time instant, I am transmitting minus x3 conjugate from transmit antenna 1, x4 conjugate from transmit antenna 2 and x1 conjugate from transmit antenna 3, and in the final instant I transmit minus x4 conjugate from transmit antenna 1, minus x3 conjugate from transmit antenna 2, x2 conjugate from transmit antenna 3. This is space which comprises of 3 transmit antennas. This is time which comprises of a total of 8 time which comprises of. So, this is 3 antennas, 8 time instants, 4 symbols over 8 time instants. So, first observe 4 symbols over 8 time instance. Hence, rate or net transmission rate, net rate equals 4 by 8 equals half. Hence, this is a rate half transmission code. This code for 1 cross 3 MIMO systems or 1 receive antenna, 3 transmit antennas, in fact transmits 4 symbols x1, x2, x3, x4 in 8 time instances. So, the net rate is 4 symbols in 8 time instance, which is 4 over 8, which is half. Hence, this is a R equals half code. So, this is a rate half code. So, this is an R equals half code. Now, what I am going to do is I am going to first illustrate how this can be written. For instance, this can be let us consider the first received symbol corresponding to this code y1 equals h1, h2, h3 into x1, x2, x3. All right, there are 3. These are the 3 transmit symbols. These are the 3 antennas. In fact, I can write this as this is h1 x1 plus h2 x2 plus h3 x3 plus I can write this as an additional plus 0 times x4. Hence, I can write this as h1 h2 h3 h4 x1 x2 x3 and a 0. Hence, I can write this as h1 h2 h3 h4 x1 x2 x3 and then a 0 at the end. Similarly, let us look at the second transmission. The second transmission y2 equals h1 h2 h3 into, remember in the second instant it is minus x2 transmitted from transmit antenna 1, x1 transmitted from transmit antenna 2 and x4 transmitted from transmit antenna 3. Hence, this is nothing but minus h1 x2 plus h2 x1 plus h3 x4 plus 0 into x3. I can write this, I can rearrange this addition as h2 x1 plus minus h1 into x2 plus 0 into x3 plus h3 into x4, and now I can write this in terms of, after rearranging these terms corresponding to the second transmission time instant across the 3 antennas, I can rewrite this in vector form as h2 minus h1 0 h3 x1 x2 x3 x4. I can rewrite this as x1 x2 x3 x4. Okay. So, proceeding similarly, I will not go through each and every simplification. I am going to directly write how the final system looks like. In the final system, I stack y 1, y 2, y 3, y 4 and y 5 conjugate, y 6 conjugate, y 7 conjugate, y 8 conjugate. I can stack this and I can write this equivalent matrix as follows. On the right hand side, I have x 1, x 2, x 3, x 4 and this channel matrix is the first row is h 1, h 2, h 3, 0, that is what we had derived earlier. The second row is h 2 minus h 1 0 minus h 3 third row is h 3 0 minus h 1 h 2. I am sorry, there should be a minus h 3 here because this is a minus x 4, this is a minus h 3, this is a minus h 3, this is a minus h 3, h 3 0 minus h 1 h 2 0 h 3 minus h 2 minus h 1 conjugate, h 2 conjugate, h 3 conjugate 0, h 2 conjugate minus h 1 conjugate 0 minus h 3 conjugate, h 3 conjugate 0 minus h 1 conjugate, h 2 conjugate 0, h 3 conjugate minus h 2 conjugate, h 1 conjugate. So, this is the final block equivalent block matrix. You can look at this. This is of dimension 8 cross 4 and that is what we expect because this is 8 time instances y 1, y 2, y 3, y 4, y 6 up to y 8 and 4 symbols which is x 1, x 2, x 3, x 4. So, this is equivalent to an 8 cross 4 hence, this is equivalent to this space time block code is equivalent to an 8 cross 4 MIMO system which is 8 transmit time instance and 4 transmitted symbols that is x 1, x 2, x 3, x 4 and this is a rate half code. Now, you can see again I will illustrate for one case that the columns are orthogonal. Let us look at C 1 Hermitian C 2. Let us look at consider C 1 Hermitian C 2, that is nothing but h 1 conjugate, h 2 conjugate, h 3 conjugate 0, h 1, h 2, h 3 0 into h 2 minus h 1 0 h 3 h 2 conjugate h 1 conjugate 0 h 3 conjugate and this is nothing but h 1 conjugate h 2 minus h 2 conjugate h 1 plus 0 plus 0 plus h 1 h 2 conjugate minus h 2 h 1 conjugate plus 0 plus 0. You see that h 1 conjugate h 2 cancels with h 1 minus h 1 conjugate h 2, h 2 conjugate h 1 cancels with minus H2 conjugate H1 cancels with H2 conjugate H1, hence this is net 0. Hence columns are therefore this is an OSTBC. Therefore this is an OSTBC, that is an orthogonal space time block code. In fact, this is rate equals half, because remember we said we are transmitting 4 symbols in 8 transmit time instance. This is rate half OSTBC, where OSTBC stands for orthogonal and this of course can be used to employ to extract third order diversity, that is to achieve third order diversity corresponding to H1, H2, H3. Remember there are only 3 coefficients. This can successfully employ to achieve third order diversity for at the receiver, and of course and the main advantage is you can achieve third order diversity without knowledge of the channel coefficients at the transmitter. Alright, so this is another example of an orthogonal space time block code. So this is an example of OSTBC. With that we come to the conclusion of the section on OSTBCs, that is orthogonal space time block codes. Next I want to go into one of the topics that we left out earlier, which is the nonlinear MIMO receivers. Remember we said we are going to tackle them later. So we are going to now look at nonlinear MIMO receivers, because that needed some background with respect to the MIMO channel decomposition and so on. So now we will look at one example of nonlinear this is an example of a nonlinear MIMO receiver. In fact, what we are going to do is we are going to look at what is known as V blast. V stands for vertical and blast stands for Bell Labs layered space time architecture. So we are going to consider the V blast technique, where V stands for vertical, B blast stands for Bell Labs layered space time architecture. So this is a nonlinear receiver. In fact, it employs successive interference cancellation. The technique it employs, V blast in general, V blast employs successive interference cancellation, which is also termed as abbreviated as SIC, that is successive interference cancellation, and the impact of each estimated symbol is cancelled from the received symbol vector. So what this roughly means is, in successive interference cancellation we estimate one symbol in the vector x1, x2, x3, x4. Let us say we estimate x1, then we remove the impact of x1 from the received vector y, and then we decode the rest of the symbol. Similarly, after decoding every symbol, we progressively remove the effect of that on the received symbol vector and go on to decode the other received symbol. This is successive interference cancellation. So because of lack of time, I will have to end this lecture here, and we will start again the next lecture at this point with a discussion of a more thorough discussion of V blast, which is vertical Bell Labs layered space time non-linear receiver architecture for multiple input, multiple output wireless communication systems. Thank you very much.